Today we want to talk about the performance of cache coherence protocols. We'll start off by classifying cache misses into 4 or 5 categories, and then we'll talk about simulations that look at the different kinds of misses that are encountered in on different benchmarks with different cache parameters. And then finally, we'll talk about physical and logical cache organization and what they have to do with performance. Cache misses have traditionally into 4 categories. The first one is now called cold misses, but originally it was called compulsory misses. They're misses that have to occur because it's the first time that a block is referenced. Conflict misses are misses that only occur because the cache is not fully associative. If the cache could fit in L blocks, where L is the number of lines in the cache, then there would be no conflict misses. But when the cache is less than fully associative, some blocks can't be kept in because other blocks conflict with them, even if they're space cache. Capacity misses occur when the cache size is not sufficient to hold data between references. And that means that, for example, if a block is at one point the 6th most recently referenced block, and there's only 4 cache lines, so you can only hold the 4 most recent blocks, then the next time that that block is referenced, that would be a capacity miss, because even if the cache were fully associative, it couldn't fit in the most recent 6 blocks just because there's only 4 lines in the cache. And the last kind is coherence misses, which are misses caused by the coherence protocol. We'll talk more about that later. The first 3 of these 4 types occur in uniprocessors, and the last is specific to multiprocessors. And the Solihin text adds another kind of cache misses, context switch or system-related misses, which are related to task switches, because it's just not realistic to assume that a process is going to run to completion on the current processor. There are a lot of other processes and tasks competing for that processor's time, and most likely when some event occurs where there's a long wait, that task will be swapped out, or maybe when its time slices up, and some other task will begin. So when a task is swapped out, then it's going to lose some of its lines in the cache before the next time it gets swapped back in, and that's why there are context switch related misses. Let's start out by looking at a small example based on uniprocessors, a cache that has only 4 lines. Let's assume first of all that the cache is fully associative, and that's significant because it can't have one of the 4 kinds of cache misses. And if you look at it, I think you can tell that it can't have any conflict misses because it is fully associative, so we know that no block is thrown out because simply it conflicts with another block in the set. It has to be thrown out because there's just not room for it in the cache. So our reference trace goes 024024680. Now, when the first 3 blocks are referenced, 0, 2, and 4, that's the first time that either any of them have been referenced, so those are all cold misses. Then when block 0 is referenced the second time, well, in this organization anyway, it's a hit. And so that's the first hit. 2 and 4 are referenced immediately thereafter. They hit in the cache as well. And then 6, when it's referenced, that's its first time, so it must be a miss, a cold miss. Ditto for 8, which is referenced next, but notice that 8 replaces 0 because the cache is now full, and we replace the least recently used line, which was a line containing 0. And then 0 is referenced, and that's a different kind of miss. It's a capacity miss, and see, that's because there are only 4 lines in the cache, but since the last time that 0 was referenced, 4 other lines, 2, 4, 6, and 8, were referenced. So there simply wasn't room for 0 to be in the cache, even though the cache was fully associative. And as you can see, there were 5 cold misses and 1 capacity miss for a total of 6 misses. So the hit rate there is going to be 3 out of 9, which isn't very good at all, but it's startup transient, so that's all we can expect. The next example is when the cache is two-way set associative. So then there are going to be 2 sets since there are 4 lines in the cache overall. One set will hold the even number of blocks when they're cached, and the other set will hold the odd numbered blocks when any of them are cached. And so you can see what's going on here, that because all of these blocks are even numbered, they all map to set 0, and that creates a little bit more conflict for set 0, as you'll see when you do the exercise. Okay, so as you see, in this case there are no hits, and there are also 3 conflict misses. Now let's look at a direct mapped cache. Blocks with numbers congruent to 0 mod 4 map to line 0. Blocks with numbers congruent to 1 mod 4 would map to line 1, but there are no such blocks in this trace. The other blocks actually are all mapped to line 2 because their numbers are congruent to 2 mod 4. And so I'd like you now to classify each of these references as a hit or a particular kind of miss. So we see here that there's 1 hit, 2 conflict misses, 1 capacity miss, and 5 cold misses. Now let's talk about coherence misses. Coherence misses can be divided into those caused by true sharing and those caused by false sharing. False sharing misses can only occur in caches that have a line size greater than 1 word, which is actually all caches. The idea here is that 2 different processes or 2 different tasks are using different words in the same line, and when one of them writes one of the words, then the whole line has to be invalidated, but the other task was using a different word, so that word wasn't really changed, but it's disappeared from the cache because of a change elsewhere in the line. True sharing misses, on the other hand, occur when a processor writes into a cache line, invalidating a copy of the same block in another processor's cache, after which the other processor reads one of the modified words. So here, the one cache or the one processor is actually modifying a word that was in use by the other process. So to summarize what we've learned, what I'd like you to do is tell me how we can attack each of these 4 kinds of misses. Just like the within process misses can be divided into 4 categories, the context switch misses can be divided into 2 categories. The first are replaced misses, which are blocks that were ejected from the cache while other processes were using the processor. And so we lost some of our blocks because the task that got run on the processor we were using just replaced some of our lines. And then there are reordered misses, which are blocks that were shoved so far down the LRU stack by other processes that they are replaced soon afterwards, when if it hadn't been for those other processes, they would have stayed in the cache. So if we have a set, let's say it's 4-way set associative, and that other task references 3 blocks that map to the same set as our favorite block map to, well, then our favorite block is at the bottom position in the LRU stack when our task is resumed. And if we end up referencing another block that goes to that same set, well, then the 3 blocks that were brought in by the other task won't be replaced, but the one that we hoped to keep in the cache is the one that's going to become a victim.